vector is proportional to negative delta x. The negative is indicating it is opposite direction, so that if I'm pulling down on this, better wording, if the slinky were displaced downwards, the force the slinky exerts is upwards. That's what the negative means. If it is directly proportional, there must be some constant of proportionality. F equals negative k delta x. This is the constant of proportionality, or in the case of springs, it is the spring constant. And we were introduced to this when we were talking about energy on the ski slope, where they stuck a giant spring at the bottom of the ski slope. So if whatever the motion is obeys this, where the force is directly proportional in the opposite direction of the displacement, then it will be in simple harmonic motion, and the motion can be described by a sine or cosine curve. So we're going to start out with an ideal coil. Hangs naturally some distance. I'll just call it x1. Actually, I want to do horizontal first. Sorry about that. I have a coil that has some natural length to it, which I'll label as x1. I'm then going to take that coil and add a mass to it. I'm not moving it yet, just attaching a mass to it, so mass M. Then I stretch it out. X2. This first situation, this is equilibrium. When I bring the mass out to here, let's force diagram. What are the forces acting on the mass?
No.
There. Not well.
Wait.
Okay.
Is it friction? It's frictionless, right?
Yeah, frictionless.
Tension?
In this case, yeah, if you could get away with that. I want to introduce sort of a new force to our formula. Ecton elastic. And only that if this is ideal, we have a formula for it, unlike tension, which is always problem specific. So keep going, F sub E. That is a subscript E, that's not just a lowercase e to indicate iron. Let's plug into Newton's second law. I know the weight and the normal force will balance each other out, so I'm really concerned with just the horizontal. Why don't we establish that as the I-hat direction. What is Newton's second law? Or what is the equation of motion?
F equals mc
F. More specifically, let's narrow it down. What is the total force? Or if we're doing the I-hat equation, what's the force?
Fe is equal to NA.
Now, since this is elastic force, we're taking the direction already into account by having a negative sign there. So we get negative K delta X. I guess technically a vector symbol. Okay, fast, we'll see some of the notation there. What I'm getting towards here is that in order to solve this, I need some equation. I have an equation for my displacement here where the acceleration is basically a negative of what I started with. If you recall, velocity is the displacement divided by time. Acceleration is the change in velocity over the change in time. In other words, velocity is the slope of position versus time, or displacement versus time as well. Acceleration is the slope of velocity versus time. So I need some function so that when I do the slope of it, I basically have a negative of what I started with. And what function, if I take the slope of the slope, gets me something that looks kind of like what I started with, or the negative of what I started with.
Is this a trig identity?
It is not. It's a trig equation.
Like, tangent? I know tangent.
Tangent is not the best one to use because tangent you shoot off to infinity and negative.
Sine?
Yeah, sine will do it. Cosine will also do it. So let's piece that together. Let me take a sine curve.
Negative cosine, right?
So this is sine of x and x. Oh, actually, doing versus time here. Time and time. I know that my slope is 0 here and here. Between them, is my slope positive or negative?
Negative.
Negative.
Out here, slope positive or negative?
Positive.
Here,
Positive.
and that's a cosine curve.
And it's negative.
If I take the slope of my cosine curve, it's 0 here, here, and here. Between there and there, is my slope positive or negative?
Negative.
And positive over here. So this is basically an upside down version of that. The pattern here is if I start with sine and take the slope, I'm going to get cosine. If I take the slope of that, I'm going to get negative sine. If I take the slope of that, I'm going to get negative cosine. Take the slope of that, I'm back to sine again. It just cycles through.
Isn't that just the derivative of sine?
Yeah.
Yeah.
Or if I start with cosine, then cosine to negative sine to negative cosine to sine to cosine. So in my equation, if my displacement can be described by a cosine curve or a sine curve, whichever one I want, my acceleration will be the negative of that. So we're going to do one other thing here. That's just normal sine, cosine. what happens if I've got y equals 3 sine of 2t? I know that if I look at the change in position over the change in time, from sine, I'm gonna get cosine, and it will be 2t. The question is, what's out front?
Which is 0, because there's no exponent.
It's not 0.
Maybe 0 because there's no exponent.
It's not 0.
6.
It will indeed be 6. Where'd 6 come from?
You take out the 2, and you multiply it.
Yeah, so when you're doing this, you're gonna end up multiplying by whatever number's here. From a graphical point of view, I started out with a sine curve. So normal sine curves, let's say, looks like that, and that's 2 pi. By putting the 2 in front, I'm basically making it go faster. I'm gonna get to my starting point faster than I did before. And so that's sine of t, sine of 2t, I basically take this and I squish it, which makes it all steeper. Matter of fact, it will make it twice as steep as it was before. And so if I do the change, the velocity, so change in velocity over change in time, well, from cosine, I'm gonna get negative sine. It's gonna be 2t, but the question is what comes out front?
Well,
So I just multiply times the 2. Multiply times the 2 to get 6, multiply times 2 to get 12. If I throw a phase shift in there, that doesn't affect it differently. So I had negative k delta x equals ma. So negative k a sine omega t. What the heck, we'll put plus phi in there. That's gonna be m times, well, remember, every time I took the slope, I multiplied by omega. So if I have a sine omega t plus phi, and that's my y, the change in y over the change in time is gonna be a omega cosine omega t plus phi. And if I did the change in time of this, a omega squared, negative sine omega t plus phi. So my acceleration would be negative a omega squared sine omega t plus phi. Negatives cancel out, a cancels out, sine omega t cancels out, and what I'm left with is k is equal to m omega squared. So if something is in simple harmonic motion, it obeys that rule that I wrote up there before. It obeys this. This is known as Hooke's law. And if it is obeying Hooke's law, it is in simple harmonic motion, and the spring constant is going to be equal to the mass times the angular frequency squared. So my angular frequency squared is equal to k divided by the mass. So omega is equal to the square root of k over m. I know that that's also equal to 2 pi times the frequency. So the frequency, therefore, would be 1 over 2 pi times the square root of that spring constant, or stiffness constant, divided by the mass. And since the period is the reciprocal of that, the period would be 2 pi times the square root of m over k. So once we can establish that we're dealing with simple harmonic motion, we've got a set of equations that immediately come into play. And there's 3 of them right there. Questions up to here? Verizon agrees with the clock there. For what, Lester?